Thank you, Rina, for giving me the opportunity to present here at your BioCARS seminar series. I would like to talk to you about some ongoing software development at BioCARS that started in 2017. And before I get into this, I would like to, as introduction, show you what sort of synchrotron experiments we are interested in and what is the aim of our work group at NIH. So we are interested in time-resolved studies of biomolecules, for example, like protein dynamics. So one of the methods we have been pioneering is the pump probe methods, like laser pump X-ray probe to study very fast kinetics in biomolecules. We have this model system, the photoactive yellow protein, which is like a bacterial photosensor. And we use this as like a showcase to develop this technique. So in brief, so we have like a protein in a nice regular crystal in a capillary, and you excite it with a short laser pulse, like 100 picoseconds, and then you probe it with a time-delayed X-ray pulse, and then record the diffraction pattern. And this is done using non-monochromatized X-ray beam. So in order to get a lot of photons onto the sample in one shot and to take full advantage of the time resolution of the synchrotron of about 100 picoseconds from the electron band structure, to get a usable diffraction image in this short time. Okay, the only way to do it is by using polychromatic diffraction, low diffraction. So we use this technique to see very short-lived intermediates in proteins, like the photoactive yellow protein. Here, for example, you see the laser-induced changes. I ran that electron density map in two colors, like the non-excited states in red and the excited state in green, and the color gradient, red to green, or magenta to green, highlights the direction of motion. So you see, for example, at the very first time point, like 100 picoseconds after excitation, there are already a lot of changes spanning the protein. You see, like around this chromophore is like a cis to trans isomerization. You see like the carbonyl chain flipping over, and you see the planar chromophore going to bend configuration, and you see the protein relaxing around it. And we took this further to make a movie out of the protein, how it undergoes to its photocycle, which takes about a bit shorter than a second or so. And you see 4 different intermediate states showing up as function of time delay. So we're going on a geometric series of time delays, and we see different structures appearing at different times. So it's like molecular movie of a protein at action. To show it more in detail, here's the chromophore region. The chromophore flips around in this half rotation and makes a full rotation from cis to trans, and then it relaxes. And then it breaks its hydrogen bonds here and locks into a different conformation, okay? Holding this protein in the signaling state. That's very important for a protein. It's not just to detect the signal, also to transmit it. And so this has to be done in a slow way. So it has to be in the signaling state for like a second or so in order to affect something, not just 100 picoseconds. So we found that in this movie, there are 4 intermediate structures represented. And using this technique of collecting many X-ray diffraction data sets of different time delays, we can map out the population kinetics of these states and assign them time constants. So we can build a population kinetical model with base maps, and then we can assign like 4 different discrete protein structures to these intermediates of the photocycle. And then we did a follow-up study with a different scheduling technique called small angle scheduling. In the first row, there are packing constraints, so we can't be quite sure the protein can really access the available conformational space in a protein. So we did a follow-up study to verify whether there may be some states we overlooked or some states that are different in solution, which is like the natural environment of the protein. And we found the same intermediates However, the signaling state has some interesting feature here, like this kink showing up. So the way we did this experiment is we collected like time-resolved scattering patterns on the same time scales. We collected our lower diffraction images and looked at the scattering, the radial dependency of the scattering, so which is transformed like into reciprocal space. And then we fitted with our existing already refined models we obtained from the lower crystallography and checked how well they agree. And indeed, we found all of them. Although the first two intermediates are really too similar to resolve with small angle scattering, there is not too much happening. But then we see the other intermediates as well. And on top of that, we can measure their time constants, which for the early intermediates agree very well, except for this one here. And then, since we have these small angle scattering data, we can also use them to do structural modeling. So we found like a signaling state in the solution, which has this large end cap moving, which we couldn't observe in the crystal for obvious reason, because the crystal, it's jammed in the crystal. It can't make these large excursions. And then we have other biomolecules interested. We're studying with small and wide angle scattering. So we are interested in protein folding kinetics. For example, we have these model systems, which are rather small proteins, and they have like specific transition points as function of temperature, where they undergo an unfolding when you heat it up or refolding when you cool it down. And we're doing this fast temperature jumps. So we excited with like infrared laser pulse, and then see how the small angle or wide angle scattering pattern evolves as function of time, and then we get a folding kinetics from this data. Not just protein, we also have some examples where we're using like model RNAs, RNA folding kinetics. So all that is performed at the Advanced Photon Source in Chicago. So at this campus outside of Chicago, at the BioCARS Beamline, sector 14. And this is how it looks like in the experimental hutch. So we have a lot of equipment in a very small hutch, especially the first thing you see, of course, is this big X-ray detector. And then, very important, a high-speed chopper to isolate single pulses. And then here, in this, if you see from the side, here's where the sample is actually. So the sample is in a capillary here. In the capillary on a translation stage. So the laser hits it from here. The laser is focused down here. It enters the hutch through a beam guide and a screen conditioning optics, and then we focus it to the sample vertically, and then the X-ray beam from the synchrotron arrives here. And for the small angle scattering, it's in the capillary. Not sure you can see this very well. We are constantly scanning the capillary to the X-ray beam to avoid like hitting the same spot twice, because that would lead to very quickly to radiation damage in the sample. It might not come across zoom very quickly, but you see the stage is constantly moving, scanning in one direction, and then rapidly retracting. So the key to this experiment is to have two pulses, a pump laser pulse and a probe X-ray pulse, that are timed precisely. So we have an electronic system that can set and change the time delay between laser and X-rays precisely. So we have, for example, fire like 8 of these pulses, and then read out the detector to accumulate more signal detector to have like to improve signal to noise, and then we would electronically tune the time delay to the next time point. See 1 nanosecond delay. Repeat this 8 times. Read out the detector, and then go to the next time delay. 10 nanoseconds. Accumulate and then read out. So this is how we make movies of biomolecules in action. So there's a lot of instrumentation behind this, making this possible. one of the challenges of the synchrotron is, although it gives us these 100 picosecond pulses, we come at a very high repetition rates, like the order of hundreds of megahertz, so or at least tens of megahertz, if like in 24-bunch mode. And this beam is also very destructive. It gives us ondulators generates hundreds of kilowatts beam. So it would evaporate the sample in an instance if we wouldn't have all these chopper trains in place. So the challenge is to isolate one single bunch out of a continuous bunch train. So say repeating every, say, 150 nanoseconds. So that requires like very demanding mechanical choppers that run at high speed in vacuum, in magnetic levitation, and need to be timed very precisely to nanosecond precision. In order to predict this sophisticated chopper, we need to reduce the heat load drastically by a factor of not 100,000, like 10,000 or so. And we have this mechanical water-cooled heat load chopper doing that, generating like bursts, so that which can then be cleaned up into single bunches by this high-speed chopper. And this is the most common bunch mode we are using at the APS. So we need like 150 nanoseconds opening and closing of the shutter to get one bunch clearly excised out of this here. Of course, we prefer this one here because there is like 4 times more photons per X-ray pulse in this hybrid mode, because they can store 4 times more bunch charge in this hybrid mode, single bunch. Unfortunately, it's just a few weeks a year we have this at our disposal. So the key thing is to synchronize all this equipment, to synchronize the two choppers with the synchrotron, and to synchronize the firing of the laser with the synchrotron and the transmission of the chopper. So all that needs to be timed very precisely. So this was my work. I already built a first generation timing system for the ID9 beamline at ESF, where I did my PhD work, but I did it actually after I finished my PhD. So because at the time the technology wasn't ready, so it is based, this is like the ESF system is based on something called a field programmable gate array. So that's like a custom programmable silicon chip where you can implement things like delay generators or pulse generators, things that like in the 1990s would fill up electronics racks. You can do that on the size of a fingernail. And what it does is takes the frequencies from the synchrotron. I mean, not the actual bunches, like a clock that indicates the arrival of the bunches that comes at 241 kilohertz, and an auxiliary clock, which is like the radio frequency clock driving the accelerators of the storage ring, which indicate like the maximum possible bunch rate, and then generate a lot of derivative frequencies, which are used to synchronize the choppers. And then once the choppers are synchronized, you can start triggering other things like a single shot opening shutter to isolate single bunches, say at arbitrary rates. For example, your Billy chopper runs at 1 kilohertz, but you would like to run, say, at 1 image per second, so we can pulse it. And then we can trigger, of course, the laser, which is very important, which is complicated though, because it has 2 stages, like an oscillator that's mode locked, and an amplifier, which is triggered on demand, and diagnostics, like the X-ray detector, the X-ray scopes. So everything is done on this piece of silicon here. It's just 10 by 10 millimeters. So it has 180,000 programmable gates, and it can form operations like counting and dividing at a maximum rate of like 360 megahertz. And we have all these programmable IOs, so which we can link to external experiments via these PNC connectors here. So each of those can generate an independent trigger signal. So one of the things that was a bit of a nuisance with the second generation FPGA is every time you wanted to add something new, okay, you had basically redesign it, adding new components here marked in red. You want to change something, a new counter. You want to change something, okay, a new pulse generator, a new delay generator. So it's a tedious process because the whole design needs to be recompiled. So which is not fast. It takes like 20 minutes, but it's always trial and error. You have to add bit by bit and check that it actually works. And you're just duplicating existing functionality for something that is very similar, but needs some extra trigger because some extra piece of equipment. So this is why we came up with this second generation FPGA. So Philip built this very nice front panel here as a printed circuit board. And here the idea is, okay, that shows operation in our lab. Here we have like 24 general purpose channels. Most of them are general purpose channel. They all have the same logic behind them. And Philip used to call this the piano player principle. So we have like 24 BNC outputs on the front. It's like a piano with 24 keys. And each of these channels can play like a track, which is like a track on this piano roll here. So you don't have to put specific design in generating these tracks. They can be synthesized by software. So you don't need a complicated set of dividers and delays and pulse generators and counters all linked together. Just one of those replicated 24 times. So for the 24 BNC front panels. So this is this design, the third generation FPGA. So we still have some core logic we need to derive lower frequencies from the very high megahertz synchrotron frequencies. So that cannot be done in software, but everything that is like below a millisecond can be done in software in a way that on this chip, which hosts the FPGA, there is also a processor, so-called PowerPC core, okay, which can run like Linux-like operating system. And in that operating system, you can have a device driver that pushes data onto the FPGA every millisecond on a clock that is the subharmonic of the synchrotron. So it's actually the same as running our high-speed chopper, like approximately 1 kilohertz. And it can reprogram each of these channels 1,000 times a second. And this way, play this sort of piano roll-like scheme, generating. Yeah, I'm just showing here 2 channels, okay. But you see a lot of LEDs are blinking, so also all these channels are actually doing something. So the design. Let me go to some details. Maybe I just want to cover briefly. So we have these 24 channels, they're general purpose. Some of them have extra capability, like very high time resolution, like nanosecond time resolution, like 1.4 nanosecond resolution, 2.4 nanosecond resolution. I can't do it for all the channels. I don't have enough space on the FPGA to route those signals reliably. So, but this is just a general channel. So which would have like 12 nanosecond resolution. And it consists out of a variable delay, a pulse generator, and a high resolution relay that is optional, and some gating. So you can operate it in 2 modes. You can just by software control turn it on and off. So you can have like a falling or rising edge every milliseconds, or you can generate precisely pulses with precisely timed edges, say exactly 486 microseconds and 243 nanoseconds after the 1 millisecond clock cycle, you want to fire it. You program this delay. And then you want to give it a pulse duration of exactly 1 microseconds. You program this delay here. And, or you can say, oh, I don't care about piano player. I will just override it. I will just manually open that shutter. Okay, that's controlled by it. So there's this gate here. And you can say, okay, I take it off piano player. I want to operate it manually. So, and I also, there is some core logic remaining for things the piano player can't do because it's too fast. For example, the Cyclo chopper requires a frequency of about 100 kilohertz to operate. So that's its encoder frequency, not its operation frequency. But it needs to be fed a signal that has the same frequency as the encoder feedback for the feedback mechanism to work. You can't trigger it at 80 hertz at the speed it runs. So it's quite demanding to phase it because you need to maintain the frequency exactly, but you can only do very small phase shift increments. Otherwise, it loses phase locks. We do this by modulating the encoder frequency by in increments of like 1 or so. I mean, in increments of 0.1%. So this way we can slowly rotate the phase and lock it into a new phase, the phaser. And the other one is the phase control of the chopper. So we have this clock from the synchrotron, which is like 271 kilohertz, called packet 0 or P0 for short. So which tells us how fast the synchrotron, the bunch pattern in the synchrotron itself rotates. And you need to lock this chopper. So you want a precise subharmonic, say of 270 something. So to run exactly at 1 kilohertz. So it always has the same phase with respect to the X-ray pulses, okay, that fly along these edges and are being chopped. Which is not straightforward because there is some jitter on that signal. So we need to do signal averaging and measure the display, and then have some software that calculates the average phase shift and then applies it, phasing everything inside the FPGA to the external synchrotron frequency. So that brings me to this second part of my talk, which is about the software to operate the Beamline. So I spent a lot of time generating these configuration tables, so which control equipment in the Beamline. So for example, there is one to configure the chopper. So what I talked about is this phase control here. So there's like a chopper phase and a phase shift. So for the different modes of operation. For example, in our favorite hybrid mode, for very high time resolution experiment, we produce this single bunch here. And then if you don't need a full time resolution, we can get much more intensity, about factor of 5 more, by using this fill pattern here. It's called hybrid fill pattern, which is like groups of 5 and 7. So that requires a phase shift here. So that is done by the timing system. And then when we don't have access to the hybrid mode, we use variable number of bunches from the 24 bunch mode because it's only 1/4. And if you don't need the full time resolution, it's of 100 picosecond, it makes sense. So for longer time delays to add more and more bunches to it to collect data faster. So this is the way it's tied together by software. So the position of the chopper, which determines the offset from the edge here, either by the opening window, and the phase set by the timing system. So this is an overview of how the software looks on the control station of the ID14V4 Beamline. So we have like a start menu which contains all the applications, and you can launch them by clicking these buttons. So the main one we are using is the one called Piano Player Acquire, or PP Acquire for short. that controls all aspects of the data collection. So how to collect the data and where to save them, basically. There are a lot of parameters, of course, you can change in a data collection. So what type of time resolution do you need? Okay, what chopper modes are appropriate for that? What's the corresponding heat chopper setting that matches that? So which time delays do you want to collect, and so on. So the idea, actually Philip's idea how to organize things is to have like a big database where all that is stored, organized in form of tables, which corresponds previous data collections we did. So they are saved with parameters in that table, so you can recall them, say the next one or 1 hour later, to exactly reproduce the data set with all its parameters. So you don't no manual typing in parameters. Okay, you can just do it at 3 a.m. in the night, see, after 24 hours of no sleep, and it still works. And the way it's done is, here is a menu in data acquisition that has a list of modes that correspond to entries in this table. For example, we want to collect a temperature jump times temperature jump data set. So it is about like protein folding kinetics. You want to heat your protein with infrared laser pulse and see how the structure rearranges itself. So in order to do that, so you have to say put a high-speed chopper in this mode here called H1, which selects a singlet hybrid. And this is just a label, but it refers to another table, which is linked to it. It's like a subtable that is responsible for the high-speed chopper mode, the one I just showed you in the previous mode. So it knows where to position the chopper, at which distance from the chopping edge the ISO beam has to pass, what's the phase setting in the timing system. And there's, of course, the heat chopper needs to be configured to match this. And then there's a list of time delays you want between the heating X-ray pulse and the heating laser pulse and the probing X-ray pulse. So it's already stored here. So it says here a linear series from 20 nanoseconds to 100,000 nanoseconds in increments of 25 nanoseconds. This is like the time series we want to cover to study the kinetics of this protein or biomolecule. So the idea is to have like a modular system that is hierarchical and extensible for controlling all the aspects of data collection. So starting with one name in this top level panel, that's for data acquisition, and then fanning out in this hierarchy of linked tables. And the only thing you need to know is, except what's the name of the method, is where to store them. You need to put in a destination directory where to store it, and then when you're ready to collect. Of course, there's some other aspects. For example, these are liquid samples. You need to load them, so you need to operate like this capillary you saw scanning. Okay, you just set it up, align it properly, put it in the beam, load the sample, or flush the capillary, empty capillary, replace the sample. So all these aspects of the sample handling of this particular sample is in this control panel. So that's just for the preparation of the data collection. So I wanted to show you what is the architecture behind this software. So you see here, this is this PP acquire GUI that is here, and there are the table GUIs here, like the high-speed chopper and the methods table. So there is an infrastructure behind it. The panels don't do anything. They are just user interfaces for servers that run in background, or as they call it at the APS, input-output controllers, POCs. So for the configuration, there's like a configuration server that has internal tables, not shown on the screen, that link to table GUIs. You can edit or make changes, or you can inspect. And behind the application, the acquisition comma, there's an acquisition server that actually executes the data collection. It's separate from the GUI. It runs as a background process and communicates with the tunnel via epics using process variables and channel access. So here, see this GUI here. So when you press, say, collect or collect data, okay, sends a command to the acquisition server that's instructed to do its job. So this is developed. You see, this acquisition server is not doing much actually. It just talks to other IOCs that are responsible for the various aspects of data collection. For example, scanning to the time points, the timing system. There's a subsystem or called delay, okay, which talks to the timing system, which generates all these packets with different time delays encoded, uploads them to the FPGA and starts playing them. So it's like a separate IOC. If you want to do temperature ramp, okay, that's also outsourced to temperature scan IOC. Other things, you can like modulate the laser power by rotating or you have a attenuator wheel, or you can scan a motor if you want to do alignment scans of your sample. Also, the way the diagnostics and the X-ray diffraction data are collected is also separate IOCs. So the role of the acquisition server is just to coordinate all this and go through a sequence. So in this table, you specify, for example, what you want to do. You want to change delay, repeat it once, and then change temperature and repeat it. For example, you can do like nested data collection, where you have several collection variables, and the acquisition server will all piece that together and put it in the right order and instruct these subsystems, okay, to actually do the job. It just monitors the progress. So that is the design principle behind it. These soft IOCs or subsystems here, it is not fully implemented yet, but they are supposed to have like a standardized interface to interact. So it's easy to make the system extensible. If you have a new piece of hardware you want to add, for example, a high voltage pulsar or something like this, you could write a dedicated IOC for this. With all boilerplate code around it, you only have to put some core code here to actually talk to the hardware. The acquisition server wouldn't have to be modified. Okay, it would just have to be made aware that there's another scan variable by adding it, linking it to the table. And this is like a modular principle of designing acquisition software, so that keeps things specialized and extensible. That's the data acquisition GUI. So, I mean, I think I already covered it. So the first thing is to select a method, then apply it, and then you have to decide where to save it by entering like a directory path. And then you have various controls, okay? Most important is, of course, acquire. So that starts the collection. You have an option to pause or resume. So if something comes up and you have the option to resume the dataset. You can interrupt it and resume it, and it will pick up exactly where it left off. And some other option Philip found useful, for example, you can say, oh, it's taking too long. Okay, you want to finish early, but you don't want to cancel immediately. You want to finish the current time series or current temperature series. So it does like a nice smooth exit. So this is why you have these controls here. Or you can add more repeats to it at the end. So now it's time for the demonstration. So I'm going to switch over to the control computer of the ID14V4 Beamline, which runs in a VNC session. So let me just build this up gradually. So we start with this menu here. So there's just one shortcut in the start menu that says here NIH BioCARS instrumentation. That brings up this menu here. And from this menu, everything is linked. So the main application is this PP acquire. Of course, there are some IOCs and servers, but already taken care of those and started them up. You see they're all running, they're all green. And let me move this here. So then PB acquire would come up, but I think I already opened it here, isn't it? To PB acquire, the first thing you do is you select a method. So you want, say, a very simple data collection, a static data collection. For example, this one here, NIH, one we used, that just collects X-ray data. It doesn't change any variables. So you can apply this here. The next step is entering a destination. So for this static one. And then we are ready to acquire the data set. So this will be like 512 images. We are not going to wait it out. Okay, I will cast it after maybe 10 or 20 to see the progress here. So you can monitor this in this directory here. If you go to the directory where it's collecting, this data box. The X-ray images, X-ray traces, and a log file that associates data collection information with every X-ray image. And it's not sure why did I say finish it here? So there's also a progress log if you want to look at what is going on. It's in the servers panel. Oh, that's the previous collection here. Well, let me just restart this here. Use data set. Acquire data set. Okay, so you see it's underway now, collecting data. So the next thing I would like to show is like a temperature ramp. So if you just tip, you do these temperature experiments, temperature jump experiments, you want to know the exact transition point of your biomolecule, where there's a structural change. So you do like a temperature scanning a range of interest, and when you're close to a transition point, okay, that's the right point to do like a time resolved temperature jump experiment, because you can only jump the temperature like 20 degrees. So you need to be in 20 degrees of your transition point. Let me cancel this and go to like a T-ramp type of position. So this is a temperature ramp from -16 to 120 degrees Kelvin, degrees Celsius. Apply this. You can also inspect it in this table here. There's like a methods table. I think it's already open. It is linked from here by pressing this button would bring it up, but it's already open here, I see. So you would see that we selected right now is called TREM. TREM from -16 to 120. This is the chopper mode, hybrid mode, selecting 56 packets. And here's the temperature range, which is like a linked subtable you can inspect. And the only variable in this scan is temperature, nothing else going on. So you see from -16 to 120 the steps of 0.5. And then at the beginning it holds the temperature for 30 images. See, so let me enter the next destination directory. So that is temperature range. And it's also nice to monitor the progress of this. We have like a temperature chart that records the actual temperature. Of course, we don't have the actual controller. This is just a simulation. So here is like the temperature controller control panel. You can just monitor the set point, set to 22 right now. So now entered a new destination here, so it should be ready to fire here. So let's see. Let me keep an eye on this log file. So the first thing it does, it ramps down to -16. Normally it takes a bit longer, but this is a simulator, so it's blazing fast, cooling down. And then it's holding the temperature of -16 for 30 images. So it's about 1 second every image, maybe 1.1 seconds. And then it will continuously adjust the temperature, ramping up to 120 degrees, so at a rate of half a degree per image. If you zoom in a bit. Hmm. Let me start this over. I don't think it's.
Well, perhaps I might interrupt, Friedrich. You've basically gone through this demonstration and kind of show how this has gone. This is a work in progress and you're refining that. Is this basically the last stage of your preparation, or did you want to show how you actually configure a new method before we open up for questions?
I wanted to also show a time resolved data collection, because let me just restart a few IOCs. Maybe that solves the issue.
But on the other hand, Friedrich, we're down to like 10 minutes for questions and answers, and maybe it wouldn't be a bad time. And then maybe some of those issues could actually come up according to questions and you could address them at that time.
Okay, yeah, okay, fine. Okay, more. So, for example, you wanted to do a similar experiment, but you're not in hybrid mode, 24-bunch mode. So what's the optimal selection for the chopper? So you would create like a derivative method of this. You would use this as a template, the one for H56, hybrid 56, DRAM. So you could, let me find it in the table here. So we have this DRAM method here. We just select this and say I want to double click this row. So, but okay, we are now 24-bunch mode. So single bunch, we want one single bunch, for example. Single bunch. Or multiple single bunches, maybe 19. So we get more intensity per image. So then you would go in here, call this here as 19. Okay, this way you created a new method, okay, by minimal editing, just giving it a new name and changing one parameter. So, and that would be usable from then on every time you're in 24-bunch mode to do the same experiment. I just try to demonstrate. I think this is what Philip wanted me to show. And but I'm not going to execute this right now. I just wanted to make sure everything works by restarting these IRCs.
Do you think 5 minutes will be enough for you to wrap up and show what you plan to do?
Sure.
Yeah, okay.
Okay, let's see. Let's start this one here. So, the next one, let me just see whether it gets started here.
I think Friedrich, it'd be good. We're really running out of time. I think you should just ramp up and then open it up for questions.
Okay, very good. So, yeah, I want to acknowledge, of course, all the people who have contributed. Of course, our NIH team. First of all, Philip, and then my colleagues Jansang and Valentin. And of course, would be possible with the support from our BioCARS team, notably Rob Henning, Bokita, and Irina. Thank you very much.